So in section 3.3 we're looking at what we call geometric sequences. We've met arithmetic sequences, that is adding on the same amount each time. A geometric sequence is timesing by the same amount each time. So that can look straightforward, 3, 6, 12, 24. I'm timesing by 2 every time. It can look a little bit unusual sometimes, so 40 minus 20, 10 minus 5. Might not look like we're timesing, but if you think about it, we're timesing, well, we're halving every time. That's timesing by a half, and the sign is flipping around. So what we're actually doing is timesing by minus a half. 40 times minus a half is 20. Times minus a half, you get negative times negative, which is a positive. So you get the 10. 10 times minus a half gives you a negative again, and it's a negative 5. Now that is not always intuitive when you first see it, but if you see a progression, if you see any sort of sequence where the sign is going from positive to negative to positive to negative, then one thing to think about is the term-to-term rule here, timesing by a negative number, because that will do the trick for us. If it's geometric progression, then if the sign is flipping from positive to negative, you times it by a negative number. If the sequence is getting bigger, if the terms are getting bigger in the sequence, then you're timesing by a number bigger than 1. And when I say bigger than 1, I mean that you're either strictly bigger than 1 or less than minus 1. So I mean the mod, or the absolute value of the number you're timesing by, is bigger than 1. Okay, so if you're getting bigger than 1 and your sign is flipping around, then you're timesing by a number less than minus 1. If you're getting bigger than 1, if you're getting bigger and your sign is flipping around, you're timesing by a number less than minus 1. If you're getting bigger and your sign is staying the same consistently, either consistently positive or consistently negative, you're timesing by a positive number bigger than 1 every time. If the terms are shrinking but the sign is staying the same, then in this case we're timesing by a half every time. If the sign is staying the same, we're still timesing by a half every time, even if the sign is negative. If the sign is flipping between positive and negative, then I'm timesing by minus a half, so a number between minus 1 and 1 if the size of the terms is getting smaller. A geometric progression then starts with a number. The next term is that number times something, times the same thing again, so a times r times r, a times r times r times r. We call it r because it's the common ratio. If you look at the ratio between any two terms, it's the same all the way, so r for ratio. And the nth term, a times r to the power of n minus 1. Nth term has this notation still. So that is where our little formula comes from on the bottom of page 66, if you're following in the book. They can ask us the same sort of questions as before. So if the second term of a geometric sequence is 4, so the second term, u2, of a geometric sequence, so that would be a r to the power of 1 from this formula. If that is equal to 4, and the fourth term it says here, so u4 is equal to ar cubed is equal to 8, then find a and r. Well, I've got two simultaneous equations with two unknowns. I can solve them. They're not linear, so substitution, or you can do something clever like the first one divided by the second one and the a's cancel out. Or the second one divided by the first one would probably be easier, wouldn't it? Because then we'll get r squared rather than 1 over r squared. And really, that's it. That's everything we need to know on exercise 3C. If you look through the examples, they ask you some other things, but if you want to stop there, if that makes sense, then I'd go for it. Because this is a video, I can do example 10 and 11 for people that are interested. So the numbers 3, x, and x plus 6 are in a geometric progression. 3, x, x plus 6. So that means if you take 3 and you times by r, you get x. If you take x and you times by r, you get x plus 6. So what you could do is say x over 3 equals x plus 6 divided by x. And that's the way they do it in the book. Another way that seems more intuitive, it's a bit more fiddly algebraically, but to me this is the way I'd think of it, is I'd think of it as 3 times r equals x. I'd think of it as x times r equals x plus 6. And then I've got two equations, equation 1, equation 2. I've got two equations and two unknowns. So I would rearrange this one, get r on its own and substitute into the other one, or however you want to solve those equations, okay? Then we can have what's the first term to exceed a certain number. So if I've got 3, 6, 12, 24, then I know that A is 3, I know that R is 2, I know that UN, the terms in the sequence are A, R to the n minus 1. What is the first term to exceed a million? So I'm saying that 3 times 2 to the power of n minus 1, it needs to be greater than a million. And you'll notice now that we're trying to solve an equation with an n is the thing we're trying to find, and it's up here in the exponent, right, in the index. So we're going to need to use our logs to solve it. If you're not happy with page 69, the blue box, then just go back to the logs chapter, which is the last chapter of the first year blue book, and it's just we're using straightforward log equation solving techniques from there. So that's it for section 3.3.